Okay, welcome back everyone. For our last contributor talk, we have Fedus, who is a PhD student at Mila, and Dibya Ghosh from Google Brain. They'll be talking about their work on MEMENTO, further progress through forgetting. Please welcome them.
Hi, thanks for the intro. My name is Fedus, and I'd like to present MEMENTO, further progress through forgetting. This was joint work with Dibya Ghosh, John Martin, Marc Bellemare, Hugo Larochelle, and Yoshua Bengio. So we'd first like to start with a motivating observation. What we're doing is we're training an intrinsically rewarded agent here. This is in Montezuma's Revenge, a difficult hard exploration game. In order to encourage exploration, we give an intrinsic reward bonus via CTS density model. As you can see, after training on 50 million game frames, the agent arrives in its dark room, has a key, and has a score of 6600. However, after additional 150 million frames of training, we're still stuck at this position of 6600. The rapid early progress did not translate into later progress. So this led us to ask, have we reached the limits of this agent? Is this architecture or algorithm limited in some way? So from this, we come with our motivating observation. We start an experiment and we say, what happens if we launch a new agent from where the last one left off, from this plateau point? And what we see is a video to the right of the agent. It starts in the room of 6600, the one that was previously inescapable. It collects the key and navigates through several rooms, and it gets to a score of 9,000. We find that this process is repeatable. You can do this over and over again, and we returned scores of 14,500 in Montezuma's Revenge. Interestingly, this new agent that's been launched from where the last one was stuck was able to escape in only 30 million game frames of training. In contrast, the original agent was there for 150 million time frames, and it was still not able to proceed. So therefore, this brings us to the title of the paper, the MEMENTO, and this is the MEMENTO observation. That is, a new agent with no memory can reliably make more progress than the original agent could. And so this is an obvious reference to the Christopher Nolan film. So this is where the main character has amnesia and has to act without any memory of how he got there or even what he was trying to do. So it's similar in this regard. So this led us to ask, what is actually happening here? There's two things that we're changing when we introduce a new agent. We're increasing the training duration, and we're also increasing the effective model capacity. Therefore, this leads to two obvious hypotheses. One, that this is due to longer training, and the second hypothesis, that this is just due to increased model capacity. To address the first hypothesis, we consider training the original agent, here shown in gold, for 400 million frames rather than the original 200 million frames. And we see that it's not able to surpass the plateau in dotted line here. So longer training was not sufficient on its own. Additionally, if we instead increase the capacity, so now we have the same capacity as the two agents, the larger model capacity is also not sufficient to break through this barrier. So again, the original agent shown in gold is not beating it, and a sweep over different hyperparameters is not effective to pass this barrier as well. So right now, we still don't have a good handle on what's actually occurring. So what we did is we decomposed the game into contexts. So per the paper Jane et al. In 2019, we're considering contextualizing the game based on the game score. And so in Montezuma's Revenge, our running example, a game score of 0, where the agent starts off, would be a context 0. A game score of 100, when the agent finally collects the key, would be context 1. When the agent finally opens the door, a game score of 400, that's context 2, and so on. With these contexts, we can now sort of track what the learning dynamics do as it trains. This is a value-based agent with a replay buffer. So what this does is it's adding tuples into the buffer, and then it's extracting them. What we can do is we can track the context of the batches being sampled. And the leftmost plot shows the fraction of the batch that's coming from context 0, and the next plot shows the fraction of the batch coming from context 1. This is Montezuma's Revenge, so it's a difficult exploration game. A randomly initialized agent is not able to make further progress. So basically, all of the experience in the buffer is return of 0. And therefore, 100% of its training is from context 0. However, as soon as the agent starts to discover the key, now the replay buffer consists of additional context, that is, those with the key. And the agent very quickly shifts towards learning about this, where now a batch basically consists of 70% from this single context. And this repeats. So now the agent learns about opening the door, and then collecting, like killing a skull or collecting other objects. So what we do is, it seems like we're seeing signatures of continual learning, but now this is actually in a single game. So this is sort of reformulating a single game really as multiple tasks. And this trend can be caused from two different things. One, the replay buffer data distribution is going to be shifting. So as the agent proceeds quickly through one stage, but then gets stuck at a frontier state, they'll spend more time trying to determine an optimal policy in a frontier state. So the replay buffer will show that difference in distribution. Also, if you have a prioritized experience replay, you're going to prioritize contexts where you had a higher error. And this is going to lead to similar like continual learning effects. So now that we've established that there's multiple phases within a single game, we can ask, how well is our agent actually generalizing across these different stages? Before, we had a completely randomly initialized agent, here again shown in blue. And what we're showing is we're launching from the plateau point that the previous one was stuck, and we show the performance of the blue agent over 200 million frames. However, if we instead use the original agent parameters, hoping that there was like some generalization, some use of all of its past memory and context, that they might improve. But it does not. There's no benefit yielded from the early parameters. And also we're finding that this observation, it generalizes to other hard exploration games in the Atari Learning Environment, including Gravitar, Private Eye, and Venture. Here where we're showing the baseline in blue and then Memento in orange. But still, this observation is just too particular, so it's one instance. What we'd like to do is now generalize that, and I'd like to turn that over to Dibya to talk about the generalization of this phenomenon to other types of agents.
All right, so far we've talked about Montezuma's Revenge, we've talked about Rainbow with CTS, and these are very particular learning algorithms in very particular environments. That is, Montezuma's Revenge and other hard exploration games, they have a narrative linear structure with sparse rewards. And so it remains to be asked, does this observation hold with different learning algorithms? Does it hold on different environments that don't necessarily possess this linear structure? What we're going to try to do is replicate the MEMENTO observation across all 60 Atari games. The first thing we need to do is discover what a plateau is. It's not as clear as in the original observation. We're going to train a rainbow agent for 200 million frames. And from this final agent, we're going to sample a single trajectory. And what we're going to be interested in is the cumulative return till date, which we're going to denote by Z. The agent might first receive a reward of 1, therefore a cumulative return of 1. Later on, another reward of 1 and a cumulative return of 2, a reward of 1 again, and a cumulative return of 3, and perhaps right before this ends, a reward of -1 and a cumulative return of 2. We're going to define the plateau point to be the point of the highest cumulative return till date. In this case, when the cumulative return was 3. And we're going to train a fresh rainbow agent with randomly initialized parameters from this exact state. How does it do? On this figure, we see a summary statistics for rainbow and the MEMENTO observation across all 60 Atari games. Each bar corresponds to a different game, and the height of each bar corresponds to the relative improvement over a baseline rainbow agent that has been trained for 200 million frames. There's two important things to note about this figure. The first is that we notice a 16.8% median improvement across all Atari games. And secondly, that these games on which we see the MEMENTO observation the most, such as, for example, Breakout or Asterix, these aren't games that have a sequential learning structure. These are games which are fundamentally different from the MEMENTO observation on Montezuma's Revenge. There's something deeper at play. We can ask if this is a result of longer training time, and we find that no, an agent that has been trained for 400 million frames using Rainbow only improves by 3.3% whereas the MEMENTO observation does far better. We can also run this exact experiment using DQN, which has far less components, working components, than Rainbow, and we find that the observation again holds here, that we get an average, a median improvement of 17% across all Atari games for DQN as well. This leads us to postulate that this is a more general phenomenon, and not just specific to any environment or any learning algorithm. To finish this presentation, we're going to talk about an end-to-end agent, a very simple one that encapsulates the general structure of this MEMENTO observation and utilizes it to avoid learning plateaus and improve progress. To do this, we're going to use a contextual agent. That is, recall from Liam's conversation that we're going to define a context to be the point between rewards. So every time we see a new reward, we're going to enter a new context. And we're going to train a different value function for each context, different parameters that are not shared, so updates can be made independently across all places. And we're going to train this entire value function architecture using Rainbow end-to-end. Bringing us back to the original example of Montezuma's revenge, let's see what happens. Rainbow by default only gets an average score of 500 across all seeds, across 5 seeds. In comparison, a MEMENTO agent, which has been trained with 5 contexts, is able to reach an average score of 2,500, not only reaching a higher score, but also doing so more robustly and faster. There's one question that remains. The MEMENTO observation has 5 times as many parameters, 5 value functions. Could this be a result of capacity? To test this, we distilled all 5 value functions that were learned in MEMENTO into a single value function with the same architecture as the original Rainbow observation. And what we find is this distilled value function performs just as well as the original MEMENTO observation. This leads us to indicate that the challenge is not the expressibility of the value functions, but rather reachability. That TD learning without this type of contextualization is unable to find desirable optima. This was a very simple end-to-end agent, and so moving forward, we can ask, there's many ways to move forward. What are appropriate measures to discover whether interference happens? We presented a simple score contextualization change, but more intrinsic phenomena might be useful to detect the presence of plateaus. We can ask, how should information be shared across contexts? We maintained independent value functions, but we might want to share more information to preserve data efficiency. And finally, in these environments which are not sequential, are there better ways to split our experience in order to choose a better contextualization scheme? To summarize, in this presentation, we gave the MEMENTO observation, that training a fresh agent which starts from the point that the old agent left off can greatly improve performance. We showed this on hard exploration games, such as Montezuma's Revenge. We showed this generalized to other learning algorithms, such as DQN and Rainbow, and across many other Atari games. And finally, we showed that this observation can help us create simple end-to-end algorithms that more efficiently escape plateaus. Thank you.